Hello everyone, Sertalp here. Welcome to the fourth part of my tutorial on how to use optimization for FPL through Python. So in this episode we will talk about how to generate alternative solutions out of an optimization model. So this topic comes up because most often than not we disagree with the optimal solution. So this could be because of your input data, maybe you disagree with some of the predictions in your data, or sometimes you would like to see alternatives to evaluate the solution from multiple angles. So whatever the reason, so we can certainly generate multiple solutions. So we can, after generating the optimal solution, we can find you the best suboptimal solution by applying a simple trick. So we will talk about this first. In the second part, I will try to cover multi-objective optimization, where you have multiple objectives in your optimization model. So this could happen when you are trying to maximize your expected points while being mindful about certain values. So this could be, so in this episode actually, I will use two objectives. The first one being our regular objective where we maximize total expected points over a horizon. And our second objective will be our expected point for the next game week. We will use multiple objectives and we will see how to use these tools to make better decisions. I have already downloaded the data from fplreview.com as we did in the earlier episodes. And here on the right side again you'll see how we will move forward, and I opened our multi-period file we generated in the last episode. Before we start, I will review what we have done in the earlier episode, and I will also mention a side thing about CBC, and then we will talk about generating alternative solutions and then multiple objectives. First of all, starting with the CBC. So in the earlier episodes, we were installing CBC through Bintray. So I suggest you to check GitHub page of the CBC solver, because apparently they have changed where they store these binaries if you are installing for Windows, for example. Also, I would like to remind you that if you have downloaded CBC already, make sure that the directory that CBC lives in is inside your path environment variable. So we generated our multi-period optimization model, and as you can remember, we were getting the data from FPL API regarding the players, which positions they play, which teams they play for, and then we were getting your team ID and then your picks from the last game week, which we were feeding into optimization as our initial input. And finally, we were getting information about in the bank amount and solving our multi-period FPL problem. So in this model, as you see, we were getting team ID, which game week you are optimizing for, free transfers, horizon, objective, and decay base as our input parameters to this function. And we had sets of players, element types, teams, game weeks, and also all game weeks, so that we can model certain constraints because we have some certain constraints that are connected with each other. And under variables, we were giving a squad, lineup, captain, vice captain, and which players to transfer and which players to sell as a binary variable to our model. So model were choosing which players to buy, sell, and then eventually put into our lineup for, and we defined this for every player, every game week, so that optimization was handling everything. And remember, we had the in the bank amount, which was a continuous variable defined for game weeks. Again, we had free transfer count, which is an integer, penalized transfers, which is also an integer, and finally our auxiliary variable, binary variable to model free transfer logic. We had our dictionaries listed. After the last episode, I added buy and sell price separately to the model using FPL reviews CSV data, so that when you are selling a player, you know that you are selling it for a cheaper price than the current buy price. And we were feeding initial conditions. We had all the constraints in the FPL problem, like how many players you can have in your lineup. You can choose only one captain, you can choose only one vice captain, and again your captain should be among the players that you have in your lineup. So these are all logical constraints here. And then we had our transfer constraints, where in order to have a player, you either need to have it from the previous game week, or you need to transfer that player. Finally, here we were modeling how to count how many free transfers you have over the multi-period problem. And finally, we had two objectives. The first objective was the regular objective, where we are maximizing total expected points, and the second one was the decade objective, where we penalize future game weeks because of the uncertainty it brings. And we were exporting problem as an MPS file and now solving with CBC, waiting for the process to complete. And finally, we were parsing the solution over here, as you see. And then finally, we were generating the data frame and printing this table at the end, and we were writing the summary of actions for understanding the decisions easily. So when we ran this problem, you might remember, but we were able to see this summary of actions because we were printing it here, and we were also exporting it to a CSV file that you can check later. So this was our multi-period model. So we checked, so we made a review of everything inside the model. I will just copy all of these inside a new file I will call decision support.py, and then I will paste everything. So starting from the top now, we will see how we can generate alternative solutions. So before I start, I received a suggestion for modeling how many free transfers a player currently has systematically. I will just copy and paste the method here and then explain to you what the logic is. Here, when we call get transfer history for a team ID, so this function is essentially reversing the game week history until finding a chip is played, or at least two transfers were made. So it's counting from that starting point, because you know that free transfers get reset if you use wildcard or free hit chips. So this essentially brings you all the transfer counts, and then this function finds if you are rolling your transfer 0 or 1, and then finally returning that value. With this change, we don't need free transfers anymore, so I will just drop this and then calculate free transfer here after finding the data as get rolling, and the first index is the rolling, either 0 or 1. If this is 0, then you have only one free transfer. If this is 1, you need to have 2. So I will add +1 here so that we can get our free transfer, and then I can delete free transfer from here. Also, let's call this sol decision support. Okay, so let me minimize these functions quickly. And remember, we were getting our merge data, team data, type data, and also next game week, and then the initial squad, and also in the bank amount by reading from official FPL API and using FPL review values. So under data, I will open preview, but essentially, so this is the data I just downloaded from FPL review starting from game week 35. And it has 36, 37, and 38, all the remaining game weeks. And in here now, we will say this function solves decision support problem for FPL. Okay, So one change I will do here is I will add an options argument here, and I will move all of these into separate options inside that dictionary. So I will say read options, and I will say horizon. For example, it should get from options, get horizon, and our default horizon will be minimum of either, let's say 3 or 38 minus next game week plus 1. So if user doesn't pass any horizon, then we can assume that the user is solving it for 3 game weeks. And then objective, here I will say objective is equal to options.get objective, and then our default value will be regular. I don't need this one too. And finally dk base, again options get dk base, and I will say 0.84 is my default value. Okay, and I can say options dict options for the FPL problem, and I will fix it later. So we are reading options here. Now, in order to have the alternative solutions, like generate multiple solutions, one parameter I will get inside options will be number of solutions. So I will call this nsols, number of solutions, options.get, and in here I will say number of solutions, how many solutions we are trying to generate, and I will make this 1 by default. So problem will remain the same. We are reading the sets, we are creating model, variables, dictionaries, all of these are the same. So the change will happen here, how I solve the problem, and then parse, and then return the solution, generating the data frame. So in order to do this, I will also generate a random problem name, because you will see that we will solve sometimes multiple problems at the same time, and I don't want this problem name to cause any issues like a collision in the name. So I will write a new function here. I will call it get random ID. This is how many characters we want, and in here I will add a new package called random, and I will return, I will join the following array I will generate. It will be random, and then I will say choice, and I need to also import string here, so I can generate a random string. For the random text, I will use letters plus digits, and then I will say for underscore in range n. So this function now will return me just a random string with n characters. So then in here, when defining my problem name, I will wait until I read options 2, and here I will say decision support horizon is horizon length, so that we can see how many horizons this is, and I will say get random ID, and then let's say 5 here, and let's see, yeah, I don't need this part too. Okay, so we will get a random problem name for every problem we will have. So the first index will only show the horizon, and then we will get a random name so it won't collide. I will also create a new folder here called output, where we will put our solutions and also the intermediate files. Okay, now let's move to the part where we will generate multiple solutions. Okay, before we go with this, let me explain what we are doing here. So in this page, as you see, we have our cell decisions on the left side and by decisions on the top. So suppose each row here is representing selling a certain player. So this is the same player you are selling, and you can buy different players for the player you are selling. So this is just a simplified notation. In this case, so all these white dots and this red dot over here, these represent your feasible solutions. So these are the transfers you can actually perform. The orange ones here are the infeasible solutions. So these orange lines represent certain constraints in your model. So this could be your in the bank amount, or maybe how many players you have from a single team. Maybe you already have 3 players, so that these players are infeasible for you to buy. So whatever the reason, there are always some players that we cannot buy even if we sell certain players, right? So here, objective direction to the top right, so that closer it is to the top right, better the solution is. So in this case, if you solve this problem, you will see that this red dot over here is your optimal solution. So again, as I mentioned, maybe you disagree with this solution. Maybe this optimal solution suggests you to buy a certain player, but you don't want to buy him because you think his minutes will be limited, or maybe you would like to see an alternative. Whatever the reason, so what we need to do here is we need to add this point to the infeasible set. So we need to say optimization that this solution is actually not the one you want. So essentially the way to do this is adding what we call a cut, so that by adding this cut you will make this solution infeasible. And then when we resolve the problem, so you will see that this yellow dot over here will be our new optimal solution. So we know that this solution is suboptimal compared to this one, but again, you don't know how much XP you are losing unless you generate this solution. With this idea, we will go back, and that's what we will do actually. You remember we already have number of solutions as a parameter here. Now what we need to do is we need to put, maybe let's create an array first so we can put multiple results, and I will say for iteration in range and solves number of solutions, then from here all the way to here I will add a tab, so that all of these steps, like solving the problem, parsing the solution, and generating the data frame, is inside the loop now. So here this part will stay the same. In here though, I will let me also create a temporary folder here so we can maybe store temporary files. I will put tmp here so that we can put the temporary files, and then after we solve the problem we can put it inside this temporary folder while running the problem. So we will clean this folder after we solve the problem and generate the data frames. In here, let's see, we don't want to disable logs for now. Before parsing the solution, I will say for v in model.get variables, I will say v set value 0. This way we will reset the solution, because since now we are solving multiple problems iteratively, we would like to reset all the variable values here. And then I am reading the problem name again. I am parsing the solution. Under here, I am generating my data frame, and we are writing the summary of actions. So here, though, I can add a new line maybe, and then say solution, and then here number it plus 1, so I can make this an f string, and another new line so that I can see which solution I am talking about. And here for w in game weeks, I am printing game week, and then let's remove these ones. Before in the bank amount, I would like to put expected points for this week, and let me create a dictionary for this. Week's XP is for W, this will be expression sum of lineup PW. For every player we will get if it is a lineup player or not, and again if that player is captain or not. So this will give us 1 plus 1 for captain 2 times points player week PW for P in players for W in game weeks. So similar to what we have here, but in this case this will be a dictionary, so it will be easier for us to refer to it, and I will say here week xpw.get value. And since this value will be a float, we don't want to display too many digits, so let's round this value to 3 digits. I think it will be enough. And then we have our in the bank amount, free transfers, and penalized transfers. Okay, this part looks good. So here, after we generate our summary of actions, it is better to print the solution here. I will say print summary of actions right here so that we can see the solution, because we will continue inside this loop, so we won't get actually a single solution, right? So I will actually even delete these ones, also this one too, and I will make this solve decision support. So only thing we will get is our team ID and then which game week we are solving for. This will be 35, and then all these will go inside a dictionary, and this is for, this is regular. And in here now, after printing the summary of actions, we will add this solution to results, our list. I will call append, and then I will add this one as a dictionary. I will say iteration will be it plus 1, and my picks will be picks df. I'm already generating here, as you see, and the objective is so remember we were already doing this. You can call model and then get objective value here, but since our objective is reversed, because we are trying to maximize, you need to multiply it with -1. So I will add minus, and I will also round this number to 3 digits, and then we will get our let's see, we will get our summary. So this will be summary of actions. Yeah, essentially this one. So, and then at the end, I don't want to return these because this will be different for every result. So I will say results will be this list of all the solutions. Okay, so now we are done with this part. Now the part where we need to add the cut. So we need to write an iterative cut here. So before, again, moving forward, we need to define what creates a different solution. Suppose I suggested you to buy this player this game week, and then buy another player the next game week, and then maybe roll your transfer in the third week. So if I only change one of these actions, suppose I suggested you not to roll your transfer in the third week, does it create a different solution for you? So what defines a different solution? So most often than not, people think a different solution is generated by buying a different player this game week. So now here I will actually use another parameter here, and I will call this alternative solution, and then this could be a thing like one game week buy. So if I change only which player I am buying for the next game week, it is a different solution for you maybe. So we will be able to change this value later. But here I will say, and also let's read this here. options that get alternative solution, and then one game week by will be our default alternative solution option. Here I will say if is equal to one game week by. Now we need to add the cut. So here, if it is one game week by, so we need to define which actions we are trying to limit. So I will say our actions is essentially expression sum of all the transfers we are making, P next game week. So remember, this is one game week, so we are only considering the next game week, for P in players, but we don't want to sum over all the transfers. We would like to only sum those transfers that we have performed. So I will say if transfer in P next game week dot get value is greater than 0.5. So in this way you are limiting, you are taking a subset of only the transfers that you have performed or the optimization found. And I will say for our game week range, it is on the next game week. You will see why we are adding this in a second. In here, okay, so now also let me also put this under an if condition, because we don't want iteration to exceed number of solutions minus 1 if it is not equal, because at the end of the iteration we don't want to solve this, or we don't want to add another cut after we finish the iteration. So in here now I will say if actions that get value is not equal to 0. So I'm adding this if condition because we might get a solution where rolling the transfer is optimal. So we will add another constraint for it, but assume that we are offered to buy 3 players, okay? So what I will do is I will sum those binary variables. Remember, those are all binary variables, so their current sum is 3. I have 3 players, so I will say summation of those binary variables should be less than or equal to 2. Why? Because this way optimization should decide that at least one of them should be 0, so which will create us another solution. So this is how we are cutting off the solution. So remember, from here we are trying to write this constraint so that this solution becomes infeasible. While we are doing this, remember, notice that when we say it like summation of these 3 binary variables is less than or equal to 2, we might be cutting off other solutions. But from your perspective, so you need to define what is the same solution. So in here you can again you can force to change your next game week transfers, or maybe you can change the entire horizon. So it is up to you, but I will show you how you can write it down. Here I will say model add constraint, because we are adding only a single constraint. So this is our cut. So I will say actions, remember this is an expression sum, should be less than or equal to actions that get value minus 1. So I will name this as my cut of, and then let's make it an F string, and then add the iteration number here. But what if optimization is already suggesting not to transfer anyone? So in this case, these actions will be an empty set, and we cannot write this constraint this way. I will say model add constraint. Here, where we will use the game week range, I will say expression sum number of transfers W. Remember, number of transfers was a dictionary we defined before. We were summing up all the transfers out, but it doesn't matter. So I will say summation of this, currently this should be equal to 0, and I will say for W in game week range, should be greater than or equal to 1. So we are forcing optimization to transfer at least one player. So what will happen then is, so suppose the original solution was including transferring 3 players. This constraint will force it to change, and suppose optimization changed it, another 3 players, and then we will add another cut. So optimization will maybe say, then transfer these 2 players, then 1 player, and then eventually optimization will say, okay, don't transfer anyone, like it is not feasible. And then at that point, we will force optimization to transfer at least 1 player. So I will name this again, cutoff underscore it. Again, this is a f string here. And after this, now, after solving the problem, let's get the results from R, and maybe we can, for I in res, in these results, we can get picks. So this is the data frame we will have, and export it to a CSV file where at the output folder, and then I will call this solution, and then let's call this let's make this an f string actually, and using double quotes. Here I will use iteration number that we passed here, and solution.csv. Okay, so we will export it to a CSV file, and then we can also create a data frame for us to see values. I will say results is equal to data frame is equal to a data frame, and here I will say create a new array with the first one being the iteration number, the second one could be maybe objective, and here actually now I'm thinking about it, maybe we can use total XP and then the next game week XP separately. So what I will do here is total XP is total XP. See, total XP is already a value here, total XP, and then next game week XP will be week XP next game week dot get value. And in here now I can get total XP. Remember, objective and total XP will be slightly different because we are also giving some weight to our vice captain. So I will say next game week XP. I think this will be enough for now. And then I will say columns will be iteration, and then objective, total XP, and then next game week XP. And then I will finally set index as my iteration. And we can actually print this at the end of our run so that you will be able to see how the solution changes. So let's do this first, and then I will show you how to use matplotlib to plot a scatter chart of it. So I'm using team ID, game week, horizon. Let's make this 3. Objective is regular. Alternative solution is 1 game week by, which is the only one we defined here. Yeah, alternative solution is 1 game week by, so this should hold true. So I will say clear first, enter this folder. So okay, let's see if this will work. I will say Python decision support.py. Already, yeah, this should be options. Okay, so this says function is not scriptable. Oh yeah, when we are getting the free transfers, we should be calling this where is it? Free transfer as a function first, and then get the first indexed. Oh yeah, we forgot to pass the team ID, and then this should be game week -1 because we need to feed the last game week as an input parameter here. Okay, so it started, as you see, it generated the random name for it, solving the problem. And then once we have the solution, you will see the summary of actions here. Okay, so this complained because I think while reading the file we forgot to add a temporary folder. Oh, we also forgot to clean the files after everything is completed. Here I will say I will put this inside a try, and then I will say, do I have padlib? Yeah, okay, I will also import padlib package so that I can locate the file and delete it if it exists. I will say padlib pad, and then we are looking for, under temporary folder, we are looking for problem name.mps file, and then unlink it again, padlib.pad f tmp problem name underscore sol.txt, unlink it, and if there's an exception we can pass it. Okay, let's see if this will work now. Okay, at least we got our first solution and then we received an error. Let's see what we are doing here. So currently it is, so we have one free transfer, and then it's using one penalized transfer to transfer 2 players, as you see here. In here it says our results. Okay, while returning it, I think I forgot to add this one. Here, as you see, I'm not calling any number of solutions, so this model should only return me this. So we will see, we should see only a data frame with one entry in it. So let's try this again, and at least make sure we can make sure that so this part is working too. And then if it is, then we will pass how many solutions we want as a as an option. Another problem here. Oh yeah, this should be iteration. By the way, I don't know if that's the problem, but let's see. Oh yeah, this should be on here. Let's see if this will work. Okay, perfect. It worked this time. As you see, I only have one solution where the objective is 213, and then my total XP is 219. Yeah, this is my total XP, but it is it doesn't take penalized transfers into account, so it's only showing me total XP without penalized transfers, and my next game week XP will be 113. So now when I add number of solutions here, this logic here should add new constraints iteratively and then resolve the problem. So I will say I want 5 different solutions. Let's see if we can generate this. So again, the first problem we are solving is the same. So we should be able to see this exact same solution again. And then in the second iteration, we will see a different solution. So just to see here, we solved the problem, and 213 is our objective value. And then second sol is going on right now. And here again it's 213 point 57, let's go back and see what was the objective. As you see, it reduced the total objective a little slightly, and we will see how it looks like at the end. And then this third solve, as you see, these solutions are very close in terms of expected points, but as you see, the decision, like which players we are buying or selling, is way different in every solve. And then I think this is the 5th iteration. Okay, so we generated our data frame here, and you see that every solution is represented in a separate file. Let me show you what it looks like. Here for the game week 35, you see your squad. Here it suggests player to sell 2 players, first one and then the second one over here, and then buy 2 new players this game week, and it shows which player should be the captain and then the vice captain. So this is the solution for game week 35, and then for game week 36 you have a different entry, and also for the remaining week. So since we are solving this problem for 3 game weeks, and then in this one, for example, let's open this one. For 35, you will see that it is showing different players to sell and buy. So let's see how different solutions are. So here we are buying 3 players, so that we are actually taking 2 hits, so it is -8, just coming from this game week. And then in the following game week, we are taking another 2 hits, another -8. So even just here, we have lots of points we are missing anyway, but here, as you see, objective reduces slightly after each iteration, like maybe even these two, as you see, they are very close to each other in terms of objectives. Let's see what the game solution 3 and 4 shows. And as you see, this is the solution number 4. We are buying 3 players, and here are the players we are buying. So at least one of them will be different in the previous solution. Let's go to the game solution 3. As you see, so we are buying different players, but in terms of expected points for the next game week, so this one is actually slightly better. So expected points is slightly higher for this one. In terms of total objective though, since we are also using the same players for the consecutive game weeks, this objective reduces very slightly. As you see, when solving FPL, we have lots of suboptimal solutions which are indeed very close to the optimal solution. This is why it is important to generate all these alternative solutions, so you can make a better assessment of it. So you can say, so this solution, for example, this solution here, even though it is only 0.2 points less, maybe this sounds like a better solution to you. And the good thing is you can also see total expected points and total next and then the next game week expected points over here, so that you can make a fair assessment of the two. Here though, when calculating expected points, let's see, total expected points and then the week's expected points, I should actually get a penalized transfer count. Let's see. It is better to reduce to, oh, we already had this one. Yeah, but this one includes the vice captain. Anyway, but I just noticed that we already have a dictionary similar to what we were trying to do. And in here, game week total is actually game week expected points with the vice captain weight, actually, minus penalized transfer. So I will use this game week total here instead of these two. So in here I will be still returning total XP, which will show us total expected points without any hits. And then we know that the objective is actually the one that carries the actual objective, where we have everything. I will add next game week objective here as game week total next game week dot get value, and then again I will round this to 3 digits. Okay, so let's also add this one to the table. After objective, this should be next game week objective. So now this next game week objective is a better value to evaluate the solution than next game week XP, which doesn't take penalized transfers into consideration. Let me rerun this, and then we can see the solutions. By the way, I will show you the temp folder, but while the optimization is going on, you will see that the files are being populated and then getting deleted because of this block here. As you see, MPS file disappeared, and then we have another MPS file here. And while this is going on, maybe I can write a separate summary of actions. So this summary of actions is for entire horizon. Maybe I can write only for the very next game week. So instead of iterating over all the game weeks, I will say identifier. Maybe I will call this next game week action is equal to an empty string at the beginning for p in players. I will first iterate over transfer in p next game week dot get value. Here I will say next game week action will add, actually let me start with by, and then here I will say plus equals, and then here I will put only the name of the player, and then maybe space, or maybe, yeah, it says maybe put this inside the list. Okay, about, and I will append the name of the player. And then here I will say next game week action minus comma join but, and then I will say I will do the same for players that we are selling. Sold for p infinite, this will be transfer out p next game we get values, and here I will say sold append, and then next game week action will be we'll say sell, and then plus this one. And then I will return next game week action here, so that we can actually get it here to show it in the table. Might be useful. Let's see, next game week action. Meanwhile, we solved the problem, but we forgot to add one minus when we are getting this week XP, I think. Let's see, next game week objectives, yeah, we don't need to multiply this with -1, sorry. But yeah, you will see that these values are very close to each other too. here. Now we are ready. So what will happen is we will also add next game week action here because we added to the dictionary. So finally we will be able to see which players we are buying and selling inside that summary table at the end. Okay, so we have the solution here. As you see, now we are able to see which players we are buying and selling. Maybe let me put a space here. Which players we are buying in every solution. So as you see, so we have different solutions at every iteration. So they are different in terms of how we defined it. We said one game week buy. So I will also add other ways to do this. I will say else, maybe elif alternative solution is equal to, maybe let's call this horizon by, and then so we will do something very similar, except we also need to iterate over game weeks for w in game weeks. In this case this should be w. So let's say summary of so let's see, actions is equal to expression sum transfer in for p in players for w in game weeks. If transfer in like this, and then our game week range will be all the game weeks here. Again, another one, elif else if so this could be, for example, one game week buy and sell. So maybe you would like to treat certain solutions where you are buying the same player but you are selling a different player. Is it a different solution? Maybe. So if you want to treat it that way, then you can add this alternative one game week buy and sell, and in here so instead of summarizing over only the buy, so let me do this. I will get this one, this, plus we will also get another one here, and then we will sum over out and then out here. So this will create again an expression. In this case we are summing two sets of binary variables, and then game week range will be again next game week. And then finally here maybe you would like to treat all the horizon buy and sell differently. So in this case again I will get this one, we already have it, so I will say plus here, this should be transfer out, if transfer out, and game week range is game weeks. Okay, so when we define it this way, now here while defining your alternative solution, so you can say one game week buy sell, or maybe horizon buy sell, so which will change, you know, your alternative solutions basically, because it will create a different cut in terms of how you are differentiating solutions from each other. So let me also put this in a slightly better format, and then here you can use one game week buy sell, horizon buy, or horizon buy sell. Okay. As you see here, we are also passing number of solutions as 5, horizon to plan for 3, and our objective regular. And in here, remember, we had two different objectives. The first one was regular, the second one was decayed, which we are using just else statement here. So you can also change this to that one. Let me take a note of it. You can use regular or Okay, I think we're done for now, but before we move forward, let me actually show you how to create a plot out of this data frame, and also I will also put this to a CSV file under output, and then maybe you can call this based on which options you are passing. I will just call this decision support solutions summary, maybe decision support alternative summary.csv, so that we can see entire action without it's getting cutting off here in the command prompt. Horizon 3, number of solutions is 5, and in here at the top we will now import our package called matplotlib here. Let's see if I have it. Yeah, I don't have it, so let me install it very quickly. Python mpip install plotlib. Okay, I installed the package. I will call this matplotlib. As you see, it shows me now. I will say pyplot as plt, and now after we solve the problem here, now we can say let's create a plot using this data frame. Pandas data frame objects have their own plot tool. I will say x is equal to maybe we can use next game week XP, and for the y coordinate maybe just the other way around, maybe total XP on the x-axis, and then next game week XP on the y-axis, and then color, let's make it blue, and then title is total XP versus next game week XP. And then finally here p get figure, and then we can save figure inside output ds alternative dot png. Okay, let's see if we can get the plot out of this. Okay, we completed this part. Let me open the plot. As you see now, we are able to see all the solutions that we have over here. So just going over the total XP without the hits or anything. So 219 is this solution over here, and I think the ones that's slightly higher is our optimal solution actually. So this is our initial optimal solution, and then the second one is actually slightly worse in terms of total XP and also in terms of next game week XP. And then the third solution we have is this one over here, and then this is the fourth one I think, and this is the fifth. Notice that we are only plotting this using XP without the penalized transfers. So it is possible to change this and use, instead of next game week XP, you can use objective for the x-axis, and then next game week objective for the y-axis for maybe a better representation instead of this one, because this suggests you that the fifth one is actually better, but maybe in terms of points you are about to collect, yes, but this solution is suggesting you lots of penalized transfers. So 2 penalized transfers over here, and another 2 over here, so 4 in total. So this you need to take a minus 16 out of this, which brings you to 213 in terms of the objective, I think. So here I will just clear this so you can replot as you want, and then I will just show you the CSV file. Let me open this. So when we generate it this way, as you see, so we see our objectives, you see they're all very close as we generated, and then the buy and sell decisions, even though they look somewhat similar, as you see, they are all different in terms of which players you are selling or buying. I think we made a mistake in the script because it's showing the same players to buy and sell. Let me check. Here, for PN players. Oh yeah, this should be solved. Okay. But anyway, yeah, you can rerun this thing. It's taking long, so I will just skip this part now. But yeah, as you see, we generated multiple solutions. We added iterative cuts, and we generated alternative solutions. So this might be valuable. Again, you can change this number of solutions to maybe like 20, and then just let it run. One thing I need to mention here is generating alternative solutions this way is very time consuming, and as you see, we are resolving the same problem over and over again. So most of the commercial solvers have this functionality, but since I work for SAS optimization, I know that our solver have this option that you can define how many number of solutions you would like to have at the end of your run. And instead of resolving the problem this way, it uses the same tree. So it is inside the algorithm. So it is much more efficient than doing it this way. So this way is kind of so the way we are doing here, like adding a separate constraint and resolving the problem, is not an efficient way of doing this, but it gets the job done for FPL optimization anyway. Okay, so moving on to multiple objectives. I will try to go a little bit faster, but when we are working with a single objective, so remember this was our total XP was our objective. As you see, this red dot over here was our optimal solution. And what we were doing before was we were adding a cut and we were getting this solution, and we were adding another cut, we were getting this solution, and so forth. But the problem is these solutions, even though they look very similar to each other, and you see that from this table over here, that they have different objective values for the next game week. So even though this solution is best overall, there are some other solutions, not here I think, but there could be some other solutions which are better than this one in terms of next game week objective. So now you're wondering, is it a good idea to maximize my total XP where I can maximize my next game week XP? And so obviously there's a trade-off. But when you add a second objective to the picture, this is how it looks like. So your previous best solution, optimal solution over here, doesn't have a really good next game week expected points maybe. So there are multiple ways to tackle these problems, but this is essentially what we call a multi-objective optimization problem. So I will mention two methods. The first one is the weight sum method, where you multiply your first objective with a parameter called w, and then you multiply the second objective with 1 minus w. So obviously if you have more than two objectives, you can have multiple parameters where the summation of those parameters should be equal to 1 in terms of how much percentage weight you are giving to every objective. And so as you see, if the w is equal to 1, then you will get the exact same solution, because obviously you are only using the first objective. So you will start to get different solutions when you start changing w. So if w is equal to 0.5, then you are giving a weight of 0.5 to total XP and 0.5 to next XP. So you are saying my next game week XP is as important as my total XP, because I would like to go for the long run, but I also maybe consider next game week XP to be important. So if w is equal to 0, obviously you are just canceling the first objective and you are just solving the problem for the next game week XP. So the second method is called Epsilon Constraint. I will call this as the two-step method because it consists of, well, two-step. So in the first step, you are solving the problem you are as is, like you are using the first objective only, and then you are getting this solution as your optimal. And then you are actually looking at the objective value and you are adding a new constraint. So this orange dashed line is my new constraint. I'm saying any solution that I will generate in the next step should have this objective at least as this much. So you are just giving some tolerance. So this is the epsilon part. So you are saying that, okay, I will move only as this much, and then you are using second objective here to maximize next game week XP. So in this case, this red dot over here will be your optimal solution. So obviously in this case though, you need to move epsilon like starting from 0 to all the way to a value that you determine, and you need to solve all those, like at every step of epsilon you need to solve two problems. So first of all, you need to solve the original problem, but then at the second step you are just adding a constraint and then resolving the problem. The good thing is this solution is always feasible for the second problem, right? So you can use this solution, the existing solution, as your initial solution to the second problem to make it go faster. So I will also talk about that one. Let's close this, and also multivariate we don't need anymore. So just for reference, I will just comment out this part so you can see what we were doing. I will talk about, let me actually put a title here. So this is generating alternative solutions. And then over here, I will call this solving multi-objective optimization. And in the first one, we are using wait sum method. So for the wait sum method, again, you need to have multiple objectives. So I will add another objective in a second. So I will say next game week XP could be one, or maybe your in the bank amount could be another one, maybe your penalized transfers. So you can define your objective as you want. In here though, I will use next game week XP. So I will add the same codes over here. I will just comment this out, and here instead of objective, a single objective, I will give a list of objectives. I will say regular and then next game week regular. Now we have two objectives here, so optimization should take these two into consideration, and then we need to pass weights. So I will say multi-objective weights, and then let's make this 0.5, 0.5. However, here, since regular XP is over, let's see, for over like 3 game weeks, and this next game week regular is only for a single game week, so these weights actually doesn't make too much sense. I mean, they're not scaled properly. So just to compensate, I will say maybe a regular game week returns you 50 points, and then for 3 weeks you will accumulate 150 points on average, let's say. So I'm just scaling. So the one way of scaling these ones is just to solve the problem to optimality using only a single objective, only for regular and then next game week regular, and then finding those values and using it for essentially dividing this weight. But in here I will just use these values, but you can feel free to play with this one. Here though, I only want a single solution for now, because we're just solving the multi-objective problem, so we don't want to generate more than one solution. And so for this one, let me delete this part too. So we have weights, we have the problem here defined. So we will talk about this part in a second, but first of all we need to see if, or what we need to do for the objective part. So remember we were using the regular objective this way and then a decay objective this way, but when we have multiple objectives, objective cannot be equal to a string, so it should be an array. So what we will do here is then we will define a dictionary of objectives. I will call this objective dictionary, where I will define regular, maybe dk, and then next game week regular as different objectives. And here I will say my regular objective is this one, and then my dk objective is this one, and my next game week one is game week total. I think this is how we defined it, right? Game week total was our, oh yeah, and then the next game week regular is game week total over here, so this should be only next game week. And then you can add different objectives, maybe like in the bank amount or number of free transfers you have. First of all, I will say if is instance, if objective is a list, then we will do something different, else it will be a simple objective, right? So in this case I will say set objective, instead of this get objective dictionary. So minus here, I will add minus here, from objective dictionary get the objective that the user requested, and then sense will be n, and then this will be a single objective. So now I don't need this part. If it is a list, then I need to find I need to get the weights and apply it. So here I will say objective weights is equal to options.get, and I will say multi underscore objective, I think, yeah, underscore weights, and then initial should be 0.5, maybe 0.5 if user doesn't pass anything. And here we will say model set objective, and here it should be sum of objective WE times objective dictionary, and then here I need to say objective as O here for IO. So the first one will give me the index so that I can read it from the weight, so assuming this is an ordered list, and the second one, second index O, will be the objective, and then I can go to the objective dictionary and get that particular objective, and I will say for IO in enumerate, and I will enumerate over objectives, and okay, and here let's see, I am adding this sum, so objective, okay, yeah, so since I already added the minus here, I don't need to do anything about it, so this should be n, and then name will be multiple objectives weighted weight sum method, so I added ws. We won't generate like more than one solution, but maybe I should add multi objective, and then this is weight sum method, solution number goes over here, and then I'm printing these ones instead of alternative. This should be weight sum, and then this should be weight sum. Okay, clear, and then let's see. Okay, We received an error immediate. Okay, forgot the comma here. Okay, so we received this solution, but we can see that this solution is essentially different from what we have received from the other one, like the other initial solution. Because of now this weighted objectives, we get a different solution. Let's see what it was for that one. So this was our alternative solutions, and this is the current one. So this one tells us to buy Fernandez and Greenwood this game week, although like none of these solutions tells us to do it. So as you see here, and my next game week objective is 113 and higher than the ones over here. And well, my objective is different now because we have a weighted objective, but we can see from the total XP that it is 222, so it is a different solution indeed. And then next game week XP, as you see, is actually higher compared to most of these solutions. So well, we can combine the two. We can generate multiple solutions under this objective, and then we can generate all of them and then plot it. Here though, what I will do is as I mentioned, I will change these weights in a for loop so that we can actually see how the solution changes. For this purpose, well, let me again copy this one and then comment this out, and then I will say this weight sum in a loop. I will use parallel processing abilities of Python. We already have, let's see, we want from concurrent features, import process pool executor, and let me come back over here, and in here I will use these options as a separate dictionary that I will iterate over, and then I will say options list is an empty list at the beginning, and I will say for s in range from 0 to 11 going 2 by 2, so that we can actually define different weights from between 0 and 1, and then we will jump from 0 to 0.2 and then 0.4. Opt clone, so I will clone the options first. So I'm preparing the input set, I'm preparing the input separately for every instance so that I can parallelize the entire thing. I will say inside this clone, multi objective weights should be equal to s divided by 10 divided by 150, again divided by 10 divided by 50. And I will say options list append optimization options clone, and now I will say with process pool executor and then max workers, let's make it equal to 16 as executor. I will say responses will be a list. Here I will say executor.map, so I will map our solve decision function, and then I will repeat. Do I have it? Iter tools? I don't. Let me import it. Import iter tools. So this tool will help us to repeat the same team ID over and over again. I will use this, and then I will, like as my second argument, I need to give, let's see, I need to give game weeks. So I will say iter tools repeat 35, and let's actually put it this way so it will be easier for us to see. And then finally here I will give options list. So now what will happen is executor will just map this function with these input parameters. So I will repeat the same team ID and same game week, and all of them will have different options because of the weights. So I'm setting weights dynamically here. And then when we solve all of these, I will get, no, I don't need this part. I will say all responses is equal to, let's make it an empty array, and then let's have a for loop here for k and response in enumerate responses, because this will return us only these solutions. So we need to match them with the inputs. But anyway, so here we will say all responses append, and in here we will actually create a separate data frame for all of those, and this will be similar to what we have here. So this will be a data frame, and then let's see how much I can use here. Yeah, this is the data frame. I will just generate it over here, and instead of res, I will use response. So because every single response can include multiple solutions, I will say response, and then I will use results. Remember, it was the dictionary we were returning. Sorry, it was the array. Remember, it was the list we were returning from the function, and columns stay the same. So the only difference here will be I will be adding k as my as an indicator of which solution we are actually getting. I will call this group. So, and then the group will be actually based on which weight we are applying here. And after this part, after we added it, we can for p in response results, we can do this part. We can essentially just put them inside a CSV file. I will call this output multi-objective WS solution, and then here let's call this group k underscore iteration.csv, and here this instead of I, this should be p. Okay, so we have these parts already added in a different format, and then finally over here, we can, by the way, print all responses, but it's better to convert this to a data frame, and I will just concatenate all responses, because this all responses, as you see, will be a list of data frames, and I will just concatenate all of them into a single huge list, and then I will print it here, and then I will put it this should be group summary, and then this should be underscore group. I think we have everything ready here. Instead of 5, let's generate 3 solutions out of all of them, and here. So when we do it this way, process pool executor will create a separate instance for every different weight over here, as you see, and all of them will run separately. So I will generate 3 solutions out of this, I think 6 different objective weights, and let's see what we will get. Comma here. And as you see, we initialize 5 problems at the same time, and then 5 problems you can see. So all of them are running at the same time over here in separate processors. Maybe too difficult to read for us, but we will be able to see the solution at the end anyway. And remember, when we are using both multi-objective and then the multiple number of solutions, we are also adding cuts so to generate alternative solutions. So this is just kind of like merging these two steps together. But yeah, let's see. Well, unfortunately we forgot to replace this one, so we weren't able to plot it properly. And yeah, hopefully I will change this one. But anyway, for now, let's see what we got here. In this one, oh yeah, we made a mistake here, so we gave the same weight to both objectives so that it came as 0. So here, instead of this one, this should be S1 minus S divided by 10, then divided by 50. Okay, this is the correct one. But I would like to show you that some of the solutions here will be same as each other, but I will fast forward this part. Okay, so we completed everything here. As you see, objective doesn't make, again, too much sense to us, but we were able to find solutions, and you will notice that most of these solutions cluster around certain values. The reason being, let me show you from here. So if a solution is already pretty good, so if it is already on this frontier, then even though we change, let me go back to the previous slide, even if we change the weight of W from 1 to 0.5, in some cases we only have like 2 points that are really good over here, and then optimization will take us to that solution. So, but as we keep it like adding cuts, and then as we force optimization to find different solutions, we should be able to get different solutions anyway. And I will open this group plot. As you see, so we only have the objective here. Objective represents kind of a weighted sum of the two. And as you see, so the solutions are actually, like, most of them are different from each other. Again, you are seeing over here. So this solution and this solution are apart from each other. So one of them is 2.27 here, and this is the one with the 2.25, I think. Yes. So as you see, the decisions change. So instead of Fernandez and Greenwood in the first iteration, it buys Rashford and Greenwood, and then it buys 3 players at the third iteration. So once we did it for all these different weights, as you see, we get different objective values, even though some of them are the same solution. But yeah, anyway, so we were able to run the weighted model, and I will talk about the two-step model now. As I mentioned before, we will solve the original problem, and then we will put an epsilon constraint, and then resolve the problem with the second objective. So for this purpose, again, I will comment this out, and then I will say this is the solving multi-objective optimization, and this is the two-step method. I will put everything back to here, and then instead of like giving objectives this way, I will also say multi-objective strategy here, and then this will be two-step, and then I need to add this one over here too, because this should be weight sum. So now this multi-objective strategy actually will go into the model so that we can differentiate which kind of multi-objective optimization strategy we are using. So I will say here, if it is a list, we were using this, right? So here I need to get the strategy options.get, and maybe we can assume that the weight sum is the default option anyway, and then I will say if strategy is equals to weight sum, this is what we will do. And here I will say else, maybe just say it this way, strategy is equal to two-step, and then here then what we will do is we will use the first objective, right? So we will get this again, we know that the objective is a list now, so we will use the first objective. I will set model.set objective, and then I will use objective dictionary objective 0, because the 0 index will give me the very first solution, very first objective. Set objective like this one, sense is equal to n, and then name is two-step objective 1. And let me just check my notes very quickly. So yeah, if it is a two-step, then I will use the first one here, and what will happen is I will just, I'm solving the problem and I'm parsing the solution and then generating the data frame, right? So instead of doing this now, after solving the problem and then parsing the solution, I will need to add if strategy is equal to two-step. By the way, I can get strategy maybe somewhere earlier. Let's see. I will just define this at the beginning, and I will say this is equal to none at the beginning, so we don't have any strategy to begin with for the multi-objective, and so this will only take a different value if it is a list of objectives. If it is two-step, then here I will get the objective 1's value is equal to objective dictionary, right? Objective 0, and then I will get value. And maybe we can also get the second one while we're here, and then maybe print it to print objective 1 value is equal to objective wow, and then objective 2 value is objective 2 value. Okay, so after this one we need to add the trade-off. Trade-off is equal to options, and then here I will get multi-objective trade-off. So this is the epsilon value I mentioned, so this is how much you would like to reduce the bound on the first objective. So let me also add this to my input here so that I won't forget. Notice that we don't need the weights here, so I will just replace this with this one, and I will say let's make it 2. So we are sacrificing 2 points from the first objective to maximize second objective. This is essentially what it means. And in here, let me go back to the if condition here. So yeah, I will get so this, let's call it this way. So if the user forgets to pass it, the user should get an error out of it. And then objective 1 lower bound now is equal to objective 1 value minus trade-off. So here though, objective 1 value is coming from the objective dictionary, which includes a minus 1 in front of it. So I will just multiply this with minus 1. So this will be a like positive value, minus trade-off will be our lower bound. And here I will add this as trade-off constraint, and I will assign it to a variable. So in the next iteration I can drop it, because I don't need to carry this objective, sorry, I don't need to carry this constraint if I'm making multiple iterations. So I will say model at constraint, and then I will say objective dictionary get objective 0. This should be greater than or equal to objective 1 lower bound, and then here name is trade-off two-step. Okay, so when we add this constraint now, we can set objective. Remember, we were using the first objective over here, so I will get the same thing actually, but here I will say use the second objective, and then this is the second objective we are solving. And then when we do it this way, now we can repeat what we are doing here. So first I will export the problem, and just because this is the two-step method, maybe I think I will be fine using the same MPS file. I think it will override, so I will just keep it as is. But here though, yeah, remember I was mentioning that when you are solving the two-step, you are using the two-step method, you can use the existing solution. So I will add a parameter maps here, and I will say use problem name underscore sol.txt. So this is the existing solution, so you can use that one to make the process go faster a little bit. And then these parts are the same, and then after this we need to parse the solution again, because the solution will be different now. So again, we will reset the variables, and then we will read the same values, and then we will generate the data frame and everything. So this should work fine, and I will just to make this go faster, I will use just a single solution, and then horizon, let's see, is 3, regular next game week, two-step 2, and we are not generating alternative solutions, but let's keep it this way. And in here, do I need to use yeah, instead of using process pull executor, you can maybe do it later. I will use the regular like regular for loop we were using here, just a regular call instead of the, I will use options as equal to options coming from this dictionary over here. Let's move this here, get results, and this time instead of wait sum, this is two-step, and then I will add two-step to this one and this one too. You can create a list, and then you can iterate over these trade-off values, maybe going from 0 to all the way to maybe 10, and then generate all these solutions. I will just cut it short here because the video is already too long. And let's see here, two-step, I added two-step over here. Next game week, I think we are good now. So we will generate on a single solution if we do it this way. And let's see what we get. At this point, I should mention to you that this is the first objective we have, and then as you see, we also printed the objective value here and here, and then this is the second objective, 113.64. As you see, after the first solve, actually this value was lower than that, but then when we tried to maximize it, it gave us the solution we want. One thing you will notice that like now this is using just lots of penalized transfers, like a massive amount of penalized transfers here, even though this is not actually correct. The reason being is penalized transfers doesn't matter when you are only optimizing for the next game week, on the next game week as your objective. So you need to be careful about some of these things in terms of solutions. Just let's make sure that we are also dropping the constraint after solving it, because we don't want the constraint to stay there if we are so we said objective 0. I think I made a mistake here. We didn't need to multiply it by 1. Oh yeah, sorry. Yeah, we had to. That's true. But we forgot to add it over here, so this should be objective 0 should be -1 times this one is greater than lower bound. Just checking the solution, I saw that the penalized transfers is a massive amount, so that I noticed that we forgot to add the -1 here. This becomes a little bit tricky sometimes, but now when we run this, I will fast forward this part. But oh yeah, just before moving forward, we forgot to add the drop constraint part, because if we are solving this iteratively here, as you see here, because I mean you can use two-step and then try to generate multiple solutions, I need to say if strategy is equal to two-step, then we need to drop model drop constraint, and then this should be the trade-off constraint. No, that is one, but the one we are adding here, we need to drop the constraint because that constraint won't have any meaning for the second iteration, for example. Running the decision support again. As you see, the second objective is 110 right now, 213 is the first one. And then when we solve it again, now it is a slightly higher value, and we have two penalized transfers the following week, the week after, and then we are only using a single free transfers. But as you see, so the initial decision I think changed slightly from one solve to another, because we know that otherwise we couldn't change next game week expected points. But yeah, that's all. I mean, we solved the two-step model too. I showed you how to do the multi-objective optimization two ways. And remember that if you need to minimize one objective and maximize the other, you can always multiply it with -1 and convert to the same sign. With this one, we concluded our tutorial on how to use multi-objective optimization and also generating alternative solutions for your optimization models. Some of the techniques I mentioned here are actually like general techniques that you can apply to other optimization models too. But I tried to talk about the FPL context on how solutions could be different from each other based on which binary variables being the key variables that we would like to change. At the end, I mean, it makes sense to just list all these optimal solutions and just make your decisions based on that. That's why I call this support decision support model, because the purpose of this model is to provide you alternatives and maybe using multiple objectives so that you can make a healthy decision based on these different performance indicators. And in the upcoming videos, hopefully I will talk more about the FPL problem, and I will talk about chips, how to include chips to the model, and I will talk about how to make like certain constraints For example, how can you force a certain player? And we will talk about all those. If you have any questions, please let me know. And as always, thanks for watching.